Well, this lecture or discussion is going to be about graphs of polynomial functions and polynomial functions in general, things that we can do with polynomial functions. So let's get started. A polynomial function, as you can see here, is a function of the form f of x is equal to a sub n, which just represents a constant number. In this case, it's the coefficient of x to the nth power. And for convenience, we're assuming that the nth power is the highest power of x, and so we could have one less power, that would be n minus 1, and that a sub n minus 1 just represents the coefficient of that next lower power of x, all the way down to a sub 0 plus a sub 0, which is just a constant. Now, we don't have to have every power of x represented, and many times we won't, but we're assuming here again that, as I've mentioned, that the n is a non-negative integer, that is, it's a positive integer. Non-negative, I suppose it could be 0. The exponent could be 0, but that would just represent a constant then, because x to the 0 is just 1. And each of the a values is just some real number. So, and the polynomial function here, as I've already mentioned, has a leading coefficient of a sub n. That is, we're assuming that the degree of the polynomial is n. That's the highest power of x. And so the coefficient in front of that highest power of x is called the leading coefficient. Even if it's not in the correct order, if the highest power of x is somewhere inside of the polynomial, then the leading coefficient is still the coefficient of the highest power of x, regardless of the order it's written in. So what we're going to do real quickly here is go through some examples of a polynomial function and then determine the leading coefficient and the degree. So here we have as you can see, a polynomial function that's negative 2x to the 5th plus 3x cubed minus 5x plus 1. We first, to find the leading coefficient, we look for the highest power of x. It happens to be at the very front, and the coefficient of that highest power is negative 2. And so that's the leading coefficient. And we also, in the same time, found the highest power of x, that's the power 5, and so that degree is 5, the highest power of x. And the next one, of course, we see that the highest power of x is 3, so the degree is 3. And the coefficient of x cubed is the leading coefficient, and that coefficient is understood to be 1. Now remember, these could be mixed up. The x cubed could actually be in a different position. Okay, well, let me get an arrow here. That x cubed could actually be in the middle here someplace, but the leading coefficient would still be the coefficient of x cubed, the highest power of x. Next example is we have f of x is equal to 14, which is just a constant. In this case then, since we, although we don't normally write x to the 0 power, which was 1, we could assume that this is 14 times x to the 0 power. So the degree is 0, and the coefficient of that highest power of x, being the degree 0, is 14, so the leading coefficient is 14. This is kind of a strange situation, but when we talk about other types of functions, it's important to recognize what the degree of a constant is. Well, one thing that we should know about polynomial functions and their graphs are continuous, and that continuous means they don't have any breaks or holes or gaps in them. So here you see an example of the graph of the polynomial function, and you can see that there's no breaks. We have little arrowheads on the end of the graph to indicate that the graph continues in each direction. We just can't draw the whole graph. Now here's another example of a function which we don't have defined, but there's clearly a break. The pieces don't fit together. This is not continuous, so it can't be a polynomial, a graph of a polynomial. And here we have another function. It looks a little different, but it is continuous. Well, in fact, let's go through this. The first graph is that of a continuous function. The second graph, because there's a break in it or there's holes in it, is not continuous. And the third graph, there are no breaks or holes, so it is also continuous. Now, we still need something to decide which of these are to be graphs of polynomials. And the other defining feature is polynomial functions are smooth. That means they have rounded terms. They don't have any sharp corners. As it says here, graphs with points or cusps are not graphs of polynomial functions. Well, cusps are pointed places on the graph. So in the very first example, the very first graph we see up there, you see that it is smooth. The corners, the turns are smooth and not pointed. And then on the far right hand, that is not smooth because we have corners. We have pointed places on the graph. Cusps are what they're called. So that boils down to that the first graph is continuous and smooth, and so we could identify it as the graph of a polynomial function. The middle graph we know is not a polynomial because it's not continuous. And the third graph we also know is not a polynomial. Although it's continuous, it's not smooth. So that's how we can tell by looking at a graph whether it's reasonable that it might be the graph of a polynomial function. Now, there are other graphs of different types of functions that are continuous and smooth, but not polynomials. But all polynomial functions have to be continuous and smooth graphs. Now, there's a certain category of polynomial functions called power functions, and that's functions that are just f of x equal x to a power, and that power has to be 1 or greater. And generally, when we're talking about polynomials specifically, the powers have to be integers, positive integers. So we're familiar with f of x equal x squared. That is a power function. We may not be as familiar with f of x equal x to the fourth. That's also another power function, and in this case each of the powers is even. And what you'll notice is the higher power of x to the fourth looks kind of like a parabola, but it's more flat down here at the vertex, and it gets steeper more quickly. And if we had f of x equal x to the sixth, it would be even more flat down here at the vertex and would get steep even more quickly. So all graphs of power functions that have even powers on x look similar to a parabola, similar. The higher the power, the flatter they are here, and the steeper they are on the sides. Now, we're also familiar with f of x equal x cubed. So we don't want to not consider odd powers, and so we're familiar with this graph already. Anytime that we have a power function that has an odd power rather than an even power, it will look similar to f of x equal x cubed. The higher the power, similar to the even powers, the flatter it is at this position, and yet the steeper it is as we go up and as we go down. So if we had f of x equal x to the seventh, it would look similar to these, but be even a more flat. And actually, it looks like it's straight across right here, but it is not. It's only equal to 0 for one value of x. So it doesn't actually stay on the x-axis, but it's very, very close to the x-axis, so it looks very, very flat in this region. Well, using transformations, then we can sketch the graphs of functions that look like this, which is a polynomial function, and we could tell that if we expanded it completely. But you can see that if we didn't have the +2 in here and the minus out here, we would simply just have x to the fourth. And so it's important to recognize that this graph will look like x to the fourth, except this +2 is going to make a change in the way x to the fourth looks, and this minus sign in front is going to make a change in the way x to the fourth looks. So we would, and what we know is that +2 causes a horizontal shift. We've already discussed that kind of thing. And since it's horizontal, it shifts 2 units to the left rather than the direction we expect. And that minus sign, since it's not on x, it's outside the fourth power operation, then it causes a reflection in the x-axis. So we would do it in that order. We'd shift left 2, and we would reflect in the x-axis then. So we'd start out with y equal x to the fourth. We'd shift that 2 units to the left, and then that result we would reflect in the x-axis, and that's what the final graph would look like, that green graph. Now, something that this is called the leading coefficient test. What we're doing now is going through a lot of features of polynomials and looking at things to see how we can tell how we can tell what the graph will look like by just having some idea of what the graph will look like by looking only at some of the features of the polynomial function itself. And this is called the leading coefficient test, but sometimes it's called determining the end behavior, and you'll see me use that terminology here in a moment. So the idea here is x gets real big in a positive way, then the graph is going to be the y value, that's the f of x, is either going to be real big positive or real big negative. And as x gets real big in a negative way, then we're thinking about x's that do this. That's what I mean. If we have x's that are way out here, then the y's are either going to be going like this, or the y's are going to be going like this. They're going to be going down. I mean, when we get real big x's, the y's are going to get either real big or real small in a negative way. Now, when we have x's that are going to the left, that is real big negative x's, then our y's are going to be either real big positive numbers, so the graph would go up, or our y's are going to be real big negative numbers, so our graph would be going down. And so on the left, our graph could be either going up or down, and on the right, our graph could be either going up or down. That's the idea about what's being said right here. I drew over what's next here, didn't I? Let's see if I can erase that. Well, let's just move on. All of this depends on the degree of the polynomial, whether the degree is odd or even, and whether the leading coefficient of the polynomial is positive or negative. That's what it all depends on. So if we look at this first graph, here's what we know. This, let me get my highlighter. This a sub n represents, remember, the leading coefficient. Okay, and what we've got here is a graph where the leading coefficient is positive. See, this, don't look at the dashed lines in here in between. Without these dashed lines, then if we had f of x is equal to x cubed, it would be going down on the left and up on the right. And so that would be when the degree, see, this n represents the degree, and this a sub n represents the leading coefficient. So here's what we're saying, is if the and think like this, if I may. Think about the way the graph of y equals x cubed. Okay, think about that graph. We know that graph is going down on the left and up on the right. And this particular graph kind of gives us the idea of everything else that's going to happen. If we have an odd degree polynomial and the leading coefficient, which is 1 here, is positive, it will be going down on the left and up on the right. That's the important thing. Now, on the other hand, if we had a y is equal to, come down here, I should have done this different. I should have done that in blue, shouldn't I? Well, I guess I've already got it here. This would be like y is equal to negative x cubed. See this red graph, because we know that flips it in the x about the x-axis, doesn't it? And so here's the idea once again. If the degree is odd, like 3, and the leading coefficient is negative, like -1, then on the left we're going to be going up, and on the right we're going to be going down. So see up here, on the left would be going up, and on the right would be going down. On the other hand, if the degree is odd and the leading coefficient is positive, like a +1, then the graph will be going down on the left, like this, down on the left, and up on the right, like this we mentioned earlier. Now, what if the degree is even? Well, think in these cases, think in this way. Let me change the color here. Think of y is equal to x squared. Now, that would be an even degree. And we know y equal x squared is a parabola, both ends point up. So kind of ignore the insides, the dashed part. There's going to be those when we get a higher degree. But what we know is if the leading coefficient is positive, see, that's what this a sub n being positive means, the leading coefficient is positive, then we know, and the degree is even, then both ends will point up. It'd be up on the right and up on the left. Up on the left and up on the right. Now, on the other hand, if the leading coefficient is negative, and we have something like y equal x squared. Let's see, where's that bright red? Y equal negative x squared. Well, then we know what would happen to that graph. We'll take that parabola and flip it about the x-axis so both ends would be pointing down. And so that's how we can tell this. If the degree is even, like a 2, and the leading coefficient's negative, like a -1, then both ends will be pointing down. So determining the way the ends point depends on two things. Is the degree of the polynomial even or odd? If the degree of the polynomial is even, both ends point the same way, either both up or both down. If the degree of the polynomial is odd, the ends point in opposite direction, left down, right up, or left up, right down. Now, how do we tell? Well, in the case of even, they both point up if the leading coefficient is positive. In the case of even, they both point down in the case that the leading coefficient is negative. Now, on the other hand, remember y equal x cubed. If the degree is odd and the leading coefficient is positive, then left down, right up. If the degree is odd and the leading coefficient is negative, then left up and right down. That summarizes what we need to know. So here we've got a polynomial, and we want to know the right hand and left hand behavior. That is the graph going up or down on the right side, up or down on the left side? And the two things that we focus on, okay, are the degree, in this case, which is 3, and the leading coefficient, which is -2. Now, we don't really care that the leading coefficient is negative, and we don't really care that the degree is 3. Here's what we care about. The degree is odd, so that means the ends point opposite directions. And the leading coefficient is negative, and so that tells us how they point. Let's summarize this. The degree is 3. We care only about the fact that that's odd. And the leading coefficient is -2. We care only about the fact that that's negative. So that would be like y equal -x cubed. The left has to point up, and the right has to point down. And that's the way I would indicate that. The left is going to point up, the right's going to point down. I'm not sure what is happening in between yet, but I know on the left it points up and on the right it points down. And in fact, this is what the graph would look like. Let's go through a few more examples here. Determining the end behavior. So here we have a function y equal -x⁴ plus 2x squared plus x minus 8. Now, if we're going to determine the end behavior, we want to know the degree. The degree is 4. That's even, so they point in the same direction. The leading coefficient is -1. That's negative, so they've got to both point down. And so it would look of this type. Okay, next. We've got a polynomial. You see g of x is equal to x cubed plus 3x squared minus x plus 5. None of this stuff out here is important. What's important is the degree, right now at least, is the degree, which is 3, and the leading coefficient, which is understood to be 1. And the fact is, the degree is odd, so they point opposite directions. The leading coefficient is 1, which is positive, so we know it looks like y equals x cubed, which means the left points down and the right points up. A couple more. Here again we have a polynomial. We scan to look for the degree. We see the degree is 5, okay, and the leading coefficient's -1. It's important the degree is odd, so the directions of the ends are opposite pointing, and the leading coefficient's negative, so that means it would be pointing in the same direction as a negative x cubed would point. So that means the left is up and the right is down. Okay, left is up and right is down. Lastly, we have a polynomial, k of x is equal to x to the 6 plus x cubed plus 1. We look for the degree, which is 6. Aha, that's even, so the ends point the same direction. And the leading coefficient is understood to be +1, so they both point up rather than down. And so that's the way we would know the ends look. Of course, there's more to figure out about what the actual function, the graph, looks like, but we know what the ends look like. Okay. A number, actually, I think in our book we talk about, rather than calling these numbers by the letter K, we call them by the letter R in our book. But a real number, K, some constant, is called a zero of a function, y equal f of x, if and only if we put that value of x, K represents an x value, if we put that value of x into the function and we get a 0 out. In other words, K is an x value that gives us a y value of 0 when we insert that x value into the function. That's all a 0 is. A 0 is an x value that causes y to be 0. It's a fancy way to say it. Really, here are the important pieces. If we've got a polynomial function and a x value, a number, okay, K, that's a 0 of f, here's what I want you to know. Here's the most important part of this. Then that means x minus that number is actually a factor of the polynomial. And it also means, remember, this is the x value, and when we put that x value into the function, we get a y value of 0. And so that actually represents an x-intercept. So K is kind of like an x-intercept, except K is just a number, and an x-intercept, remember, is a point that has an x value and a y value. So these three conditions are equivalent, basically, that if K is a 0, K comma 0 is an x-intercept, and x minus the number K is a factor. So in other words, if 3 is a 0, then x minus 3 is a factor of the polynomial. Or if -1 is a 0, then x minus -1, which would be x plus 1, is a factor of the polynomial. That's a critical issue. Turning points on a graph of a function is a point where the graph changes directions, changes from increasing to decreasing or vice versa. And we can predict the number of turning points a graph might have by looking at the degree. And as you can see here, a polynomial function has, of degree n, has at most, not exactly necessarily, but at most n minus 1 turning points. And at most n zeros. Okay, so that says if we have a quadratic function, f of x equals something x squared plus other stuff, then the degree is 2, so it can only have 1 turning point, and a parabola does in fact have 1 turning point. And it would have at most, because the degree is 2, at most 2 zeros. So here we're to find all of the zeros and the number of turning points of the graph of f of x equal x cubed, excuse me, x to the fourth minus x cubed minus 2x squared. Well, the first thing we would do is factor it completely. And what I'm noticing to do this is that we have a common factor of x squared, so when we factor x squared out, see what would happen when we factor x squared out. And of course I've already got it here, but when we factor x squared out, whoops, we would have what? X squared minus x minus 2 left. And when we factor x squared minus x minus 2, we would get x plus 1 times x minus 2. So there's our x squared that we also factored out. So there it's factored completely. Now, the real zeros are the numbers -1, 0, and 2. Now, why is that? Well, because remember, let's take the -1. It comes, you know, if what we would be doing is we would want to know what causes, let's see if, let me go to the next slide here, okay? What causes f of x to be equal to 0? Remember, the zeros are the x values that cause, whoops, that's ugly, isn't it? I'm sorry, this is a tool that I'm not too used to. The x's that cause the y to be 0. And so we would be solving this equation. Here's f of x. We've got it above, but now I'm trying to write it here. Sorry about this. I'm apologizing. I'm trying to write with my mouse and rather than what I've done in the past, and that's very difficult to do. So we're solving this equation. That's what we're doing. And we can see that if x is 0, then this would be true. What we would do is we would take each of these factors and set them to 0 separately, wouldn't we? We'd take x squared and set it to 0, and we'd take x plus 1 and set it to 0, and we'd take x minus 2 and set it to 0. And then we would solve each of those. Well, for x plus 1 equals 0, the solution is x equal -1. And for x squared, excuse me, for x minus 2 equals 0, the solution is x equal 2. Now for x squared equals 0, we could actually think of that as x times x equals 0, and the only way that can happen is if x is equal to 0. So those three numbers being the solution to that equation are called the zeros. And so this 0, x equal -1, corresponds to the x-intercept -1 comma y equals 0. Okay, so this is the x value, the 0, and this is the y value that that x causes to happen. Remember, the zeros are the x's that cause y to be 0. Now here's the x value, that's the 0 we have up here, and we know that's going to cause the y to be 0 because that's what we solved. And this x value is the 0 that we have here, and that we know is going to cause a y to be 0. So these 3 points are the x-intercepts of the graph. This is what the graph looks like, and you can see that here is the x-intercept -1 comma 0. Here's the x-intercept 0 comma 0, and here's the x-intercept 2 comma 0. And what else do we know? Look at this. This is kind of important here. We know it's a degree 4. Whoops. We know it's a degree 4, and we know the leading coefficient is 1, so both ends point up, and that's exactly what we've got here, isn't it? Now, we may not have known everything else, but we had that much information, so at least it's reasonable the way this graph is looking to us. Oh, now, the graph shows that there are 3 turning points. Okay, see, there's a turning point, as it says right here. There's a turning point right here. There's a turning point. There's a turning point. Changed directions, didn't it? Changed directions right here. Started going from up to down, and here it went from down to up. So there are 3 different turning points. The degree is 4. The maximum number of turning points is degree minus 1, or in this case 4 minus 1, and it in fact had 3 turning points. Okay, repeated zeros. This is kind of hard to read, and I'll read it, of course. If m is the largest integer for which x minus k to the mth power is a factor of f of x, and m is greater than 1, then k is a repeated zero of multiplicity m. All it means is once we factor the polynomial, if it has a factor that's x minus a number to some power other than 1, the power on that x minus k is called the multiplicity of the 0k. And the reason that's important, remember those zeros, k represents a 0, those zeros are places where we cross the x, or where we touch the x-axis, they're x-intercepts. And so the significance here, we'll have to see some examples for this to make sense, I think. But if this power on that factor is odd, then the graph, we know the graph has an x-intercept at k comma 0. We already know that because k is a 0. But what we don't know is how the graph acts, and this is what it's telling us. It goes across the x-axis there, but it wiggles, kind of like x cubed wiggles as it goes through the origin. On the other hand, if this power m is an even number, then the graph doesn't go through the x-axis, it touches the x-axis like y equals x squared does. It looks kind of at the intercept represented by k comma 0. So it looks kind of like a little parabola at the intercept. So for instance, well, here's what it's asking us to do. Determine the multiplicity of the zeros. And so we've got a function f of x equal x minus 2 cubed times x plus 1 to the 4th power. It's already in factored form. So we need to determine the zeros. And of course, we can tell the 0 right here by what causes this what x value causes this factor to be 0. And if we replaced x with 2, that would be a 0. So the 0 is a 2. What's the multiplicity of that 0? Well, the multiplicity of that 0 is this exponent we have on that factor, 3. And that's odd. That's an odd multiplicity. So what happens? It crosses the x-axis at the intercept 2 comma 0, but it looks kind of like a little x cubed. So it crosses the x-axis doing something like that, or doing something like that. Now that's assuming the x-axis is like this. So it wiggles as it goes through the x-axis. Okay, well, what about the next 0? Well, we look at this next factor. Here's the next factor, x plus 1. And we want to know what x causes that factor to be 0. And that x value would be -1, isn't it? So the next 0 is -1. Now, what's the multiplicity of that 0? Well, it's this exponent that's on that factor. So the multiplicity is 4, which is even. So what does that mean? Well, it means it touches the x-axis, okay? It touches the x-axis, but doesn't go through it at the x-intercept -1 comma 0. See if I can get an eraser to get this stuff off of here. So here's something like the graph would look like, and it's important for us to recognize here. So remember, we had because the 0 was 2, we knew the x-intercept was 2 comma 0, that's right here. And we knew that the graph, the multiplicity there was 3, so at x-intercept the graph kind of looks like a little x cubed graph. Now the 0 of -1 means we have an x-intercept of -1 comma 0. That's right here. And the multiplicity of that 0 is 4, which is even. Okay. Now if it's even, then it looks kind of like a little parabola. It doesn't go through the axis, it just touches it. So you can see that's what's happening here, right? At that position, it looks like a little parabola. Now, what if the multiplicity were 1? If the multiplicity were 1 at a particular place, then the graph just goes straight through, just like normal. It doesn't wiggle, although it looked wiggly there for me. But the graph would go straight through and not have either of these special features. Okay, that's if the multiplicity is 1 rather than something bigger than 1 that's odd, or something that is bigger than 1 and is even. So here we're asked to sketch the graph of f of x equal 4x squared minus x to the fourth using the information that we know. Okay, so before we get too far into this, let's notice some things. We know, let's look at the degree. The degree is 4. Aha. So that means the end behavior, both ends point the same direction, but the leading coefficient's -1, isn't it? So that means both ends point down. So on the left, whoops, it's going to point down, and on the right, it's going to point down. We already know that before we get very far into this. Okay, let's move on. Well, we'll write the polynomial function in standard form, which just means where you rearranged it. And now we really haven't done anything significant there except we rearranged it. We can still tell that the leading coefficient is 4, and excuse me, the leading coefficient is -1, and the degree is 4, which is even. And we've already discussed that. So, and this is a fancy way to say what I said up here with my arrows. The left points down, the right points up, and that's what we see down here, kind of starting the graph. Okay. Well, what do we do next? Find the zeros. Well, to find the zeros, we'll factor it. In this case, we factored out a -x squared, and when we factor out a -x squared, we'll be left with x squared minus 4. And x squared minus 4 is the difference of two squares. We'll factor as x plus 2 times x minus 2. Okay. Now, we actually have 3 zeros. This factor gives us the 0, x equals 0. This factor gives us the 0, x equal -2. This factor gives us the 0, x equal +2. Now notice, though, there's one other thing. This 0, which goes with this factor, okay, look at the exponent on that factor. The exponent that gave us the 0, x equals 0, exponent is 2, multiplicity 2. So that tells us that we're going to have a different feature of the graph right there. Okay, so this is just a repeat of what I've already said. We have 2 zeros, -2 here, -2, and +2 here. Okay, that comes from these two factors. And each of those, because the exponent on the factor is 1, those each have a multiplicity of 1, which means at those positions, here's where -2 is, and here's where +2 is. The graph is just going to go right through the x-axis, nothing special. But at the where we have the 0, x equals 0, that's going to be associated with a x-intercept that's right here. And because the multiplicity is 2, we're going to have something that looks like a little parabola right there. So we have the x-intercepts -2 and 0, a -2, 0, and 2, 0, and just crosses right through. Okay, and at 0, 0, it touches only. So we have these ideas. Now, here, you know, in this case, we know that it touches. It could have touched from below instead of from above like it does here. But the other information tells us that it has to touch because it's going to be above the axis here, so it has to be this shape. Let's go on to the next page. Now, we could also easily plot the y-intercept, and to do that, we would choose x to be 0 and solve for y. Okay. And then we could plot some additional points. We could choose x to be 1 and get y of 3, and choose x to be -1 and get y of 3. So we have all of this information. We have some kind of idea of the shape. We know it points down on the left and down on the right. We know it goes right through the axis here. It goes right through the axis here. Since we know we have these points and these points on the graph, then it has to be a little parabola pointing up rather than a little parabola pointing down at that x-intercept. So we have a pretty good idea of what this graph looks like. Now, notice also that we have 3 turning points. Here's turning point 1, here's turning point 2, here's turning point 3. Since the degree was 4, we could have predicted 4 minus 1, or at most 4 minus 1 turning points, or 3 turning points, which is what we have. Finding the tops of these points that I've got highlighted right up here, where the graph turns around, that's really a calculus issue. Where does that happen? We don't really know that x equal 1.5 gives us that top value where it turns around, or negative 1.5. That's something that we have to wait to do until we get to calculus. Okay, well, let's try to put some of this stuff together to finish out this lecture. And occasionally we're asked to find a polynomial function that satisfies some given conditions. Now, in this case, we're asked to find a function f that's defined by a polynomial that is degree 3. So it means x to the 3rd power is going to be the highest power of x. And it has the zeros -3, -2, and 5. And in addition, we know that when x is -1, y is 6. That is, f of -1 is equal to 6. So how do we approach this problem? Well, the first thing is remember that if k is a 0, remember that's what we said in the beginning, if k is a 0, then x minus k is a factor. So here we have -3 is a 0, so x minus -3 is a factor, and of course that's x plus 3. So x plus 3 is a factor. Now here we have -2 is a 0, so x subtract -2 is a factor. Well, x subtract -2 is x plus 2. So x plus 2 is a factor of this. And finally, since 5 is a 0, then x minus that 0 is a factor. So x minus 5 is a factor. So we have the 3 factors already determined. Here's one of the 3 factors. Here's one of the 3 factors. Here's one of the 3 factors. Whoops. So we know this polynomial looks like f of x is equal to some constant times x plus 3 times x plus 2 times x minus 5. These factors are fixed. Now, there's a infinite number of polynomials that have these 3 factors. So there's an infinite number of polynomials that have these 3 zeros. But if you change the number that is in front, if you change this leading coefficient, if you will, if you change this number right here, okay, then each time you change that, you'll get a new function and it will have a new graph. But they'll all go through the x values of -3, -2, and +5, every one of them. But some will have the left pointing up and the right pointing down. Some will have the left pointing down and the right pointing up. There's all kinds of different ways they could look depending on this value of a. But what we need to do is find the value of a that's required if we're going to have f of -1 be equal to 6. In other words, if we put -1 into the function, we get a 6 for y. So that's the big deal. Well, so since we will solve for a by already knowing that we have the requirement that if x is -1, y is 6. So that means we put -1 in for each of these x's. -1 in for each of these x's. That's what I've done below. And we know that result has to be 6 because we know that f of -1 has to be 6. And all we're doing here is looking at -1 plus 3 is 2. -1 plus 2 is 1. -1 minus 5 is -6. So we actually have 2 times -6 is equal to a times 2 times 1 times -6. See, here's a 2. Here's a 2. Here's a 1. Here's a -6. So when we multiply those three numbers together, we get this -12 times this a that we already have. And so we simply solve for a by dividing on both sides by -12. We get a is -1/2. And so the polynomial is, now we know a is -1/2 times x plus 3 times x plus 2 times x minus 5. And if we were to multiply all of that x plus 3 times x plus 2 times x minus 5 out and multiply by -1/2, then we would get the result -1/2 times x cubed plus 19/2 times x plus 15. That is the single polynomial that has the 3 zeros above, is degree 3, and if we put -1 into the function, we get a y value of 6 out. Okay, let's do one more similar to that. Find a function f defined by a polynomial of degree 3 that has 4 as a 0. That's what that's supposed to say. Whoops, wrong thing here. 4 is a 0, and the multiplicity of that 0 is 3. And if we put an x value of 2 in the function, we get a y value of -24 out. But the idea is that if we have, very simply, if we have a 0 that's 4, then x minus 4 has to be a factor. And since that factor has a multiplicity of 3, that means x minus 4 has to occur 3 different times. And of course, we'd just say x minus 4 cubed. Now, again, like before, anytime we have a different a value, we'll still have 4 as a 0 of multiplicity 3. But we need to know the specific a value that will cause y to be -24 when x is 2. So we go through the same kind of thing we just went through. We know that f of 2 has to be, if we replace x with a 2, because f of 2 has to be -24. So if we replace this x with a 2, that's what we've done here, then we know that the y value we're going to get is -24. Well, 2 minus 4 is a -2, and we cube that, we get -8. So the right-hand side is -8 times a. We solve for a by dividing by -8. We get a is 3. So f of x is a, 3, times x minus 4 cubed. And if we were to expand that, multiply it all out, that's the result we would get. I think that brings me to the end of this lecture, and I think it ought to help you get your homework done just fine. So we will stop here.